This week's real shift is that reinforcement learning for LLMs is getting much more precise. Instead of spraying one reward signal across an entire answer, researchers are now fixing where that signal goes, across objectives, across score ranges, and even across individual tokens. That matters because most alignment failures come from bad credit assignment, not just bad data. What ties these results together is a move from blunt optimization to controlled, variance-aware learning, and the payoff is stronger reasoning with fewer training pathologies. Let's explore the first paper, DVAO Dynamic Variance Adaptive Advantage Optimization for Multi-Reward Reinforcement Learning. DVAO, or Dynamic Variance Adaptive Advantage Optimization, is an Alibaba cloud proposal for multi-reward reinforcement learning in large language model alignment that targets the failure modes of standard GRPO scalarization. The paper argues that reward combination can inflate squared advantage magnitudes and destabilize policy gradients, while advantage combination with static weights ignores cross-objective correlations. DVAO replaces fixed weights with variance adaptive weights proportional to each reward's empirical rollout group standard deviation, so high variance objectives receive more learning signal and noisy low variance objectives are suppressed. The authors prove two key properties. DVAO bounds advantage magnitude relative to raw reward combination and introduces an implicit cross-objective regularization effect, with sensitivity depending on the combined rollout performance rather than isolated objective scores. Experiments use Quen 3, 4B, base, and Quen 3, 8B, based on mathematical reasoning benchmarks, AIM 2024, AIM 2025, Math 500, Olympiad Bench, and AMC 23, plus Quen 2, 5, 3B, Instruct, and Quen 2, 5, 7B, Instruct on BFCL, V4 tool use. DVAO reaches the strongest average trade-offs, such as 47.49 accuracy and 99.92 length compliance on Quen 3, 8B base, and 63 accuracy, with 79.21 average format compliance on Quen 2, 5, 7B, Instruct, while dominating the Pareto frontier across weight sweeps. Training uses DAPO, Math, 17K, Tool RL data, group size 16, batch size 128, 500 steps, Atom W at 1E6, and 8,192 token generation. Let's explore the second paper, Discretizing Reward Models. Discretizing Reward Models, from Carnegie Mellon University and Meta Superintelligence Labs, argues that continuous reward models can be dangerously oversensitive. They often assign different scores to responses that are equally useful, which creates exploitable reward gradients in RLHF. The paper separates reward quality into discriminative ability and specificity, showing that popular models such as Skywork 5.1, Skywork 5.2, GRM, and ARMO-RM can score highly on standard benchmarks, yet still fail this tie-sensitive criterion. The core result is that a training-free discretization method, reward clustering, uses Monte Carlo dropout to estimate reward uncertainty, hierarchically clusters response scores, and maps clusters to ordinal bins. In the theory, an optimal midpoint threshold can preserve perfect discriminative ability while eliminating oversensitivity in the binary case. On Reward Bench 2's ties subset, clustered rewards improve the average of discriminative ability and specificity for all four reward models, with Skywork V1 rising from 70.8 to 74.9 and GRM from 69.2 to 80.6. In a mixed reward IF-evil simulation, discretization suppresses over-optimization of spurious hedging rewards, and in a verifier-free multitask RL setup on 30K, prompts each from RLVR IF-evil, RLVR Math, RLVR GSM, and WildChat, discretized rewards were never significantly worse than raw rewards and often much better. The method adds only a modest 15% runtime overhead during GRPO training while using 8 H100 GPUs and 4 dropout samples. Let's explore the third paper, GRAIL Gradient Reweighted Advantages for Reinforcement Learning with Verifiable Rewards. GRAIL, from Declare Lab at Nanyang Technological University, is a token-wise credit assignment method for reinforcement learning with verifiable rewards that replaces GRPO's uniform sequence level advantage with gradient activation saliency. Instead of paying for a process reward model, it backpropagates the final answer loss to the input embeddings, computes a first-order saliency score per token, log scales and standardizes those scores, then clips them into a bounded reweighting scheme before the policy gradient update. Across 5 models from the Qwen 3, DeepSeek, R1, Distill, Llama, 8B, and OctoThinker families trained on DeepMath 103K, Grail improves average accuracy by 3.6% and pass at 3.3.05% over GRPO on 6 math benchmarks. With especially large gains on AIM 2024, Qwen 3 8B rises from 36.67% to 47.78% accuracy, while OctoThinker 8B rises from 2.22% to 4.44%. The method also beats OARG, reaching 62.04% average accuracy on Qwen 3 8B versus 55.75%. A Wilcoxon signed rank test reports W equals 459.5 with P equals 1.3 times 10^8, and the paper notes a 50% to 60% training time overhead on 4 times NVIDIA H200 GPUs, trading compute for finer-grained reasoning alignment without step-level supervision. That's a wrap on today's AI paper highlights. Thanks for watching.